Good morning all, how are you doing? Okay, today we'll continue still talking about regression analysis. Okay, previously, if you remember, we talked about simple linear regression. In simple linear regression, this is the line that is supposed to represent the relation between the independent variable x and the dependent one y. This equation has two parameters, which are beta naught, which is the y-intercept, b1, which is the slope, and of course we know that the error is epsilon. What is important for us is the two parameters beta naught and beta 1. This relationship or this equation is supposed to represent the relation between x and y in the population. And usually beta naught and beta 1 are unknown. That's why we go and draw a sample and use the sample to estimate this equation by the following one. Y hat equals b naught plus b1x, where b naught is the y-intercept and b1 is the slope. B naught will be is used to estimate beta naught, of course, and b1 is used to estimate beta 1. What we're going to do today is to talk about what we call multiple regression analysis. A multiple regression equation is an equation that shows the relation between several independent variables and one dependent variable. In the simple linear regression case, we have only one independent variable, which is denoted by x, and one dependent variable, which is denoted by y. In the multiple regression analysis or the multiple regression equation, we have several independent variable and on the other hand only one dependent variable. According to this, we have in this equation a number k of independent variable x1, x2 till xk, and the equation is y equal beta naught plus b1 x1 plus beta 1 x1 plus beta 2 x2 till beta k xk plus, of course, the error part. So y is the dependent variable or the response one. X1 is the first independent variable or the first predictor. Beta 2 is the coefficient of the second independent variable, and so on till beta k is the coefficient of the independent variable number k. This equation will be estimated based still on sample data. As we know, beta naught, beta 1, beta 2 till beta k are all unknowns. These are the parameters of the original regression equation. If we are talking about the population, usually they are unknown because we're not dealing with populations. We have sample data. So based on the sample, we can estimate the equation to be y hat equals b naught plus b1 x1 plus b2 x2 plus till bk xk. Y hat is the predicted value for y or the predicted dependent variable y. B naught is the y-intercept of the equation that depends on the sample data, which will be the estimator of beta naught. B1 is the slope of the first variable x1 in the equation that is calculated or that is estimated based on the sample data, and it will be the estimator of beta 1 and so on. Now we're going to use an example. In this example, we're talking about Jenny Wilson, who wants to develop a model to determine the suggested listing price for houses based on the size and the age of the house. So, okay, this guy, Jenny Wilson, has a real estate company, and they want to compose a model or to form a model to represent the price or the selling price of the house, okay, in terms of the size and the age. So it's like the price depends on the size of the house and the age of the house. So the estimated equation should be y hat equals to b naught plus b1x1 plus b2x2. Y hat is the dependent variable, which is the selling price, of course. B naught is the y-intercept. X1 is the first independent variable, which is the size of the house, and it is measured in square feet. And X2 is the second independent variable, which is the age of the house. B1 is the slope of X1, and B2 is the slope of X2. Okay. So Jenny Wilson started by selecting a sample of houses that have been already sold, and here are the data. So we have in the first column the selling price, and it is measured in dollars. Okay. In the second column, we're talking about the size measured in square feet, and then the age in years. Okay. In addition to this, they added a column for the condition of the house. Some houses are in good condition, some are in excellent condition, some are in mint condition. What we care about in the equation that we're going to estimate is to represent the selling price, okay, as the dependent variable, and on the other hand, we'll have the first independent variable, which is X1, to represent the size in square feet, and the second independent variable, which is X2, to represent the age of the house. Let's move directly to what are we going to do in this case. As I said previously in the first part of the simple linear regression, you won't be asked to do any calculations, okay? So this will be what you can face in a case like this. What we do is we take the data that has been presented by the table we saw in a moment, and we plug it into our software. Here we use Excel actually, which is very easy to use. Yani it's on every computer. And we got this out. So your rule will be mainly to how to read this output. From this output we can get many things. The first thing that we will need to get is the equation itself. The part that you can use to write the equation is the part here, down here. This last table. Okay, so this is where you can find the regression coefficients. Okay, now how are we going to compose this equation? Here it is. Y hat is equal to, you will find that okay, first thing here, the intercept. So what is the intercept? It is this value. The intercept is B naught. Okay, so we take this number and write it as the first number. And then I'm supposed to have, so this will be B naught, and then plus B1 X1. We know that X1 is the square feet or the size. So we'll move to, here it is. Here is the coefficient of X1. And then X2 is the age of the house. Here is the coefficient of the age. So now I can, from this table, I can get the equation. I can compose the equation. This will be your first target when you look at the output. To compose the equation, how to write it down in other words. So y hat is equal to the intercept plus b1x1. b1 is the coefficient. So you will find all the values of b naught, b1, and b2 in the column titled coefficients. Okay, so we'll start with b naught and then plus b1, which is 43.82x1, plus b2, which is negative 2898.96 x2. Now let's move to how can I read this equation, or how can I interpret the values that I have in this equation. First thing we need to do is to write the interpretation of b1, which is the coefficient of x1. b1 is equal to 43.82. If you remember, what was the interpretation for the slope? The slope of the independent variable is always the rate of change in the value of y when x increases or decreases by 1. So let's say now that x1 is the size of the house, correct? يبقى according to this, if the size of the house increases by 1 unit, which is 1 square feet, okay, then the selling price is supposed to increase by 43.82 since B1 is positive. Now the question that we need to ask ourselves is, in our equation we have two independent variables. So now if I want to interpret the coefficient of x1, I cannot neglect the coefficient of x2. That's why I cannot interpret b1 without mentioning anything concerning the second variable x2. So usually in multiple regression, here is how you can interpret the coefficients of the independent variable. If I'm interpreting the value of b1, okay, which is the coefficient of x1, I'm going to say that this is the change in y that happened as a result of a change in x1 by 1 unit, okay, while x2 didn't change, or assuming that x2 is constant, it never changed. Okay, if I want to interpret the value of b2, I'm going to say that this is the change in y that results from a change of 1 unit in x2, assuming that x1 didn't change, and so on. So now let's see in our case. x1 is the size of the house in square feet, and x2 is the age of the house. So if I want to interpret the value of b1, which is 43.82, I'm going to say that if the size of the house increases by 1 square feet with no change in the age of this house, the selling price is expecting to increase by the amount of $43.82. Let's move to interpreting the slope of x2, which is negative 2,898.69. In this case, we have a negative value, so this shows a decrease. So now we can say that for every additional year in the age of the house, okay, with no change in its size, the selling price of the house is expected to decrease by $2,898.69. So this is basically how you can interpret the slopes of the different independent variables. Now let's move to the interpretation of the y-intercept. Actually, the y-intercept is a quantity that sometimes when we interpret it doesn't give us any practical meaning. And sometimes it is very important. It shows a piece of information. So if it shows a piece of information, good. If it doesn't, we simply use it to draw the line, to have a good representation for the line. So let's see in our case what happens. How can I interpret B naught? The value of B naught here is 146,630.89. Now, usually the y-intercept is the value of y when x is equal to 0. Now, here we have two x's. So mathematically, I can say that this is the value of y if both x1 and x2 are equal to 0. This is from a mathematical point of view. Now let's talk about our case. So we can say here that if the house is new, correct? Because the age is 0, it's new, okay? It's in the plan, in the process of being built, for example, and it has no size, which is size equal to 0, which basically doesn't make sense, of course. Then the price is expected to be $146,630.89. This interpretation is a bit theoretic. It doesn't, practically speaking, it doesn't have any meaning. It doesn't make sense. So now, how can you think practically about this value, or from a practical point of view? We can simply say that if the house is new, okay, and under construction, it's like we have the plan of the house, but it hasn't been built yet, which happened for a real estate companies. They can sell the houses before constructing them. So the price is expected to be $146,630.89, which means that this price can be considered as the starting selling price for the houses in this company, actually. And this was our equation. So now we saw the equation and we saw the interpretation of the equation of all the coefficients we have in the equation. Now, second thing we need to do for this equation is to do an assessment, like what we did in the linear regression case. So we have two tools, if you remember, which are the coefficient of determination, R squares, and we have the ANOVA table that is used to test the significance of the relation. So let's go back to the output another time, and let's see how we can do the assessment of this equation. So let's start with the ANOVA table. In the ANOVA table, we have here the value of what we call the significance. If you remember, we said this will be the p-value. How can I do the test? I use this number, which is the p-value, and I will compare it to alpha. Usually, alpha is assumed to be 0.05 or 5%. Now, if you remember, the rule is, if the p-value is smaller than alpha, we reject H0 and accept H1. And if the p-value is larger than alpha, we accept H0, which means that we reject H1. Now, let's go back and refresh our memory. What is H0 and H1? In this case, which is the case of multiple regression, H0 is always the model is not significant, which means that we are assessing the whole model, not every beta, not beta 1 and beta 2. So we're simply assessing that the model is not significant. and H1, or the alternative hypothesis, is the model is significant. Now, in this case, since p-value is smaller than 5%, then we're going to say that we reject H0 and accept H1, which means that this model is significant. Now let's move to another value that is important for us, which is R squared. R squared here is equal to 0.67. Now, how can I interpret R squared? Now, when we were talking about simple linear regression, we simply said that R squared is the percentage of change in Y that are explained by the changes in X. Now, since here I have more than one independent variable, so we can simply say in this case that the value of R squared, which is 67%. Here is how I can interpret R squared, or the coefficient of determination in this case. I will simply say that the model explains 67% of the variation in the selling price, which is Y. In the multiple regression case, we say that the R squared represents the percent that the model explains, okay, from the variations in Y. Let me repeat this another time. I'll phrase it in another way. R squared in the case of multiple regression will show me the percentage of the variations in the dependent variable that are explained by the model. Okay, so now in our case, this model explains 67% of the changes of the variations that happened in the selling price of the houses. Taban, this is an indication that this model is a good one. Let's move to another test we can do, how we can read from this output. So far, let's repeat it another time, or let's take another look. From the output, I can write the equation. Now, writing the equation means that I can, in the second step, interpret the coefficient of the equation. And then I can do an assessment for the equation. So how can I do the assessment? I can do it by two ways. I can test the significance of the relation based on ANOVA. So if the p-value is smaller than alpha, we say that we can reject H0 and accept H1 that say that the relation is significant. If p-value is larger than alpha, we accept H0, which means that the model or the equation is not significant. The second way to assess our model is to look at the value of R squared, or the coefficient of determination. In the case of multiple regression, R squared will give me the percentage of changes that happen in the dependent variable that are explained by the model. And then let's see what else can I do. How can I read from the output of a multiple regression case like this one? We can test individually two hypotheses. The first one, that beta 1 is equal to 0 against beta 1 is not equal to 0, which means now that I can test the significance of beta 1. And I can also test the significance of beta 2. Now, how can I do this? We know that B1 is the estimator of beta 1. So now we will move to the right, and here is the p-value. The p-value, so the test concerning beta 1, which is the coefficient of the size, gives me a p-value which is 0.0013. Of course, when I compare this value to alpha, I will directly reject H0 and accept H1, which means that beta 1 is not equal to 0. So this means that beta 1 is significant. Now, if I want to test the other coefficient, which is beta 2, H0 will be beta 2 equals to 0, and H1 will be beta 2 is not equal to 0. So we will use B2, which is the estimator of beta 2, and then here is the p-value corresponding to the test of beta 2, or significance of beta 2. The p-value is equal to 0.0039. Still, this p-value is smaller than alpha. Then this means that we're going to reject H0 and accept H1. So beta 2 is significant. Actually, these two tests are t-tests. But as I said before, we won't be doing the tests manually. You're simply going to read the output and interpret on the results. Okay, now this is what we said, the F-test or the ANOVA test, and our square to assess, and then to determine which independent variables are significant, we perform the test for beta 1. H0 is beta 1 equal to 0, again it's beta 1 not equal to 0. We take the p-value and compare it to alpha. Since it is smaller than alpha, we're going to say that beta 1 is significant. And the same will be for beta 2. So as a summary for this example, we can say that the model is significant because the p-value of the F-test of the ANOVA is smaller than alpha, and R squared is 67%, which means that the model explained about 67% of the variation in the selling price. Okay. Now, to test the significance of each of the coefficients of x1 and x2, we calculate the p-value for each case, okay, and we test the significance. The p-value for x1 and also for x2 are smaller than alpha, which means that they are significant.